All right, let's start again. So I'll take two questions. There was one question here in the room that I saw, somebody raising their hands, another question on Zoom. And then I'll also get back to this a question asked earlier about no reduce function. So let's start with who wanted to ask a question at the front? I saw raised hands. No longer? Did anybody in the lecture hall had a question to ask? The end of the lecture? Yes, go ahead. So the question is whether we get the benefit of collocation of the data in the query if we use the split procedure right here. Yes, indeed, you do, because so the fact that there are 3 replicas, if you consider that the splits are the blocks in HDFS, every block will have replicas stored on 3 different machines. So it gives you some flexibility. Now, the idea is that when you grab the next task, you can optimize that further by trying to grab tasks for which you have data on the same machine, right? As one example of the optimizing it, right? So for a while, you will be able to do that. Towards the end, maybe no longer. At the end, maybe you will have to read over the network. Or the opposite, maybe you have so many idle machines that it's easy to ask for the idle machines to take new tasks for which they have data, right? If you have one task left, just pick the machine on which the data is, which will be idle. So this kind of works well in practice. I mean, this is why the technology was so popular. But again, the idea of bringing the query to the data in collocation is most of the time, but occasionally you might have to read from the network, right? It might not always work, right? Does it make sense intuitively? Okay, there was a question on Zoom too.
Yep. In this specific use case, would you not maybe bucket the postcards differently rather than in equal weights? Directly proportional to each person's speed, assuming you have control on how you allocate the tasks.
So this is basically an alternate possible design that MapReduce could have been done with. It's the idea to try to have tasks of multiple sizes, and in order to match them to the slots. I could totally imagine that we could try to write a technology like this. What you lose, however, is simplicity. The idea of having tasks or splits or like even sizes, and then a certain number of slots that are smaller, and then let dynamically the number of tasks per slot vary, is simple. It is very simple, and it evolves dynamically in a way that works. So you might be able to optimize in a different way and optimize the sizes here and so on. But the extra engineering work that you would put into this might not necessarily give you a better performance than using this technique. So you really have to weigh the pros and the cons. It might be that this is both simpler and already with several multiples of slots for the number of tasks is already really not so bad. And it works no matter what the input is, right? Okay, go ahead. Aha, that is a question on tail latency, right? A lot of you are curious on tail latency. So you're absolutely correct. And in fact, it's not only that it can happen, it's that it will happen. As soon as you have thousands of machines or 10,000 machines, the more machines you have, the more it is guaranteed that one of them is going to take forever. I will come back to this in a few weeks because this is super important. And the lesson here is really that when you start running into these issues, that one of the machines is going to take forever, it becomes totally useless to optimize your map function and your reduce function. You might be tempted to say, okay, I'm going to make my map function, my reduce function faster and so on. You're going to reorganize a little bit. It will just not work because the problem of the tail latency is really something that is tied to the size of the cluster. At this scale, you start experiencing these problems no matter what. And on the Moodle forum, this was discussed because in the Dremel paper, they write a little bit about that. One of the several solutions, because there's many ways to solve that, one of the solutions is to just, okay, say, if that machine takes longer, just ignore it. We drop it, we ignore the data from that machine, and we just make do with the other, with the rest of the data. The results will not be quite correct, right? Because you will ignore that part of the data, But maybe because of your knowledge and field domain knowledge of what you are doing, it might be that you're totally fine having only 98% of the data, right? Imagine that you're computing statistics and then you're dropping 2% of the sample. If you assume that it's completely random, then it doesn't matter. You get less precision maybe, but it still works. So this is one of the ways. But this is a very good question because indeed it will start happening. And at large scale, you cannot avoid it. It's just there, right? Okay, so that's a very good question, and I'll have a full lecture discussing these things in a few weeks. This is a very exciting topic. All right, so let me take, oh no, before I continue, and then you can still ask questions later, but I have to continue with the lecture. I want to go back on something we discussed. You asked about, is there a way of just having no reduce phase and not shuffling at all, right? And the answer is, and that's actually, it kind of makes sense. Indeed, there is a way to tell MapReduce, there is no reduce phase, there is no reduce function, and it's called a map-only job, right? Map-only job. So there is a way, I think you just submit null to the setReduce function, and then there is no shuffling, there is no reducing. The output of the map phase is directly written to the to HDFS. And that's actually very convenient for debugging, because if you have a problem in your MapReduce job, just drop the reduce phase, only execute the map phase, and inspect the output of the intermediate key values on HDFS, right? Okay, all right. So now to the terminology, having used the postcards, and that should help a lot. What is a map function? The map function is the implementation of the function in Java or Python or whatever. It's the function that takes one key value as an argument, one, and that maps it to 0, 1, or more key values. And how many depends on your code. You are writing the code, right? So this is your function. But this is a function. It's called for one key value. The reduce function is also an implementation in Java. It takes one group of key value pairs, so one key and a list of values associated with that key, and we assume that these are all the values associated with the key. Then you call the reduce function, and it returns 0, 1, or more output key values, right? So this is the reduce function. In that case, it's almost math, right? It's mathematics. It's a mathematical function that takes key values and returns key values, both the map and reduce function. The combine function is the same. It's also a function that takes key values and that returns key values. But what the combine function does, it always maps to the same types. The type of the input is always the same as the type of the output. And unlike the reduce function, for the combine function, you might have only a partial set of values. In fact, you will most often have only some of the values associated with the key, but there might be some other values somewhere else with the same key, right? The reduce function never happens. You're guaranteed that all the values are there. Okay, so this is about the function, map function, reduce function, combine function, right? Then what about the task? The task is really a to-do. It's a homework. It's something you have to do. And what a map task is it is the homework of repeatedly calling the map function on all the key values that belong to an input split, right? So a map task is the to-do, the homework of repeatedly calling the map function on every key value in one input split. For whom does that make sense? Okay. And the calls are sequential, right? A task, it's sequential. When you write your postcards, every person sequentially write the postcard. It's not like Alice is writing one with the left hand and another one with the right hand. Maybe people can do that, but I can't, right? So it's really sequential. So you really have this, and then this, and then this, and you just go down. Typically, it's going to be thousands of them in the same split. So it's the repeated call sequentially of the map function on all the key values in an input split. And it results, then you merge all of them back. It results in many intermediate key values, right? That is a map task. The reduce task, now you probably guessed what it is. It is a to-do, a homework of repeatedly calling the reduce function on groups of key values, the intermediate data, but grouped by key, right? So key by key, all the keys that belong to this reduce to this partition of what we reduce, we call the reduce function, then we call again the reduce function, it's another key, then we call again the reduce function, it's another key, and so on. Again, this is sequential, right? The task is sequential, executed sequentially. So you see that here we have a one-to-n, right? There are multiple calls of the map function in a map task and multiple calls of the reduce function in a reduce task. That probably answers the question one of you asked earlier, right? Can't remember exactly who asked what question, but one of you asked whether the relationship between the functions and the task. And again, there's multiple function calls in a task and multiple reduce function calls in a task. For whom is that clear? All right. So far, we are at the task level. What is a combined task? Who thinks it doesn't exist? Everybody raise your hands. Combined task doesn't exist. Exactly, it doesn't exist at all. We have a combined function. It's called during the map phase when you flush, when you want to compact. There is no such thing as a combined task. Doesn't exist. That's the reason why combiner is a very bad idea. You shouldn't use the word combiner. Okay, so that doesn't exist. We don't have combined tasks. All right, now, so this is just the illustration. The combine is really used maybe at the end of or during a map task to compress the output of the map task, right? That's what it's used for. Okay, now let's go one more level. I'm going to talk about the slots now, the map slots, the reduce slots, and so on. What is a slot? Well, I put this little image on the top to show you the hardware, right? We are here talking about some memory in there, and this is one core. It is one core, or maybe a virtual core, if you want to go to that level, that is going to sequentially process tasks. It's like Alice sitting at the table, processing one batch of postcards, and then a second batch of postcards, and then a third batch of postcards. In the same way, my slot, my CPU, is processing a task, and then processing a task, and then processing a task. This is, again, sequential. It's sequential within the task, that within each task, the function is called sequentially. And it is also sequential outside of the task because the tasks are taken care of one after the other by the virtual core, by the slots, right? At that point, there is no parallelism at all, right? We're talking about just one virtual core that is sequentially executing the map function, but it's nicely batched because this is all done task after task. For whom does that make sense? Right? So you see the virtual core is just repeatedly calling the map function. And now we might be looking at millions of times here. Okay? Okay, all sequential. The reduce slot is the same thing. We have again one virtual core. It's processing a reduced task, then it's done, then it's processing another reduced task, and then it's done, and then it's processing another reduced task, and so on until none is left. There is no parallelism. It is all sequential. Sequential within a reduced task, that the reduce function is called sequentially, and also across reduced tasks, that the reduced tasks are executed one after the other on a specific virtual core. For whom is that clear? Very good. So now it starts probably adding up, right? The function, the task, the slot. Is there such a thing as a combined slot? No, there is no such thing as a combined slot. Very good. Okay. Now, what about the map face? I'm zooming out even more. Now, of course, I don't have a single virtual core, right? I have a data center maybe with 1,000 machines, and on every machine, there's maybe 16 virtual cores. So that's like 16,000 slots, right? So what's going to happen is that all of the slots, all of my virtual cores, they're going to work now in parallel, right? So there is slot number 1, slot number 2 might be another virtual CPU on the same machine. Slot number 3 might be another machine, and so on. But within every slot, it's all sequential. But since we have multiple slots, they do it in parallel. Now, these are like the people writing the postcard, the slots, and the tasks are just the to-dos on the batches of postcards. Okay? For whom does that make sense? Who thinks that it's clear now what's going on? Okay. It's very important to understand, again, what's sequential and what's parallel. What's parallel is between the slots, but within a slot, it's all sequential. Okay, and the same goes for the reduce phase. We have multiple virtual cores here, multiple reduce slots, and they all within the slot, it's all sequential, but since we have multiple slots, this is all done in parallel. Okay. Okay. Is there such a thing as a combined phase? No, very good. You're following. Awesome. So there's only the combine function, and that's the only thing we have. So now, if I show you this picture, we have the machines, a node. We have multiple slots, the virtual cores, and each slot processes tasks sequentially, and within each task, you have sequence of function code and so on. So this is how it all works. Now, just to make it even more precise, and here I'm talking about the first version of MapReduce, because then I'll talk about version 2. So the first version is what I've shown you with the job tracker, the task tracker, and so on. And what's done is that the slots here, the virtual cores, before the job runs, we decide this virtual core is a map slot, this virtual core is a reduce slot, and so on. So it's all decided statically. Statically means before we actually run the job. So ahead of time, we say, this is allocated for mapping, this is allocated for reducing. Okay. All right, so this is what I wanted to show to you, and this will be relevant for Apache Spark as well. I'll come back to it on Apache Spark, but all of that now is just, once you have learned it, then you know it, and it's reusable. Now I would like to come back to a question that one of you asked actually last week. It was a very clever question that you noticed. So a task is a map task or a reduce task, but what I told you is that in the case of the map tasks, every map task corresponds to one split, right? And every split roughly corresponds to an AGFS block. And the reason I'm saying roughly is that it's not exact. It's not exact because when you consider an AGFS block, it's exactly 128 megabytes, except the last one. But every other block is 128 megabytes. And then you stop exactly at that 1 byte, you cut it, and then comes the next block. But a split is a collection of key values. So if you consider a split, it's more on the logical level. You don't have key values and then half of a key value. That doesn't make sense, right? You can only have full key values. So it means that when you look more into details on what happens, you will have, so here I have the physical level, the blocks in HDFS. I have here my split, so I have the records, and a record here might correspond to a key value pair logically, but it's going to be stored somewhere. And now imagine that now we are half between these splits here, or let's say the last one of that split. What's going to happen is that from a physical perspective, it starts at the end of that block here, and then the next bits are on the next block. So we have a record, a key value, that is now spread over 2 blocks. So what that means is that a split and a block is not quite exactly the same thing. It's almost the same thing, but not quite exactly the same thing, because the last key value you need to finish from the other block. So that's a remote read, right? You might process all of the key values that are in there, and then the last one you need to finish from the next block. And there is an optimized way of just asking for the first bit here in order to finish processing it. Like you don't have to read the whole block, okay? That's all implemented. So now you basically have this picture where every split finishes a bit on the next block and so on and so on. And then you know for the next block, you start with a small offset. You start reading like from here to process the key values in there. All right, for whom is that clear? Okay, I'm not going into the details of how this is done. There's a clever implementation in Java that allows you you can override it if you want to supply your own way of partitioning the data. But this is basically how it works. So this is the end of the MapReduce part, MapReduce version 1. And I hope it made sense to you. So now I'm going to stop here unless there is a question, maybe an opportunity, 1 or 2 questions. Who understood everything or almost everything on MapReduce? Lots of raised hand. On Zoom as well? Is anybody here on Zoom? Is anybody listening to us? Raise your hands if you're following. Okay, we have raised hands. Awesome. And no questions on Zoom. Okay. So I'm going to stop here and I'll see you on the other side where I'll take over for Spark.